Hello everybody and welcome in this second videos about virtual time sensitive network V-TSN, presented by me, Fabien Bouquillon, and my colleague Donato Ferraro. We are researchers from Unimore, the University of Modena and Reggio Emilia, and more particularly from the HIPERT lab, the High Performance Real-Time System Laboratory. And also this laboratory has two spin-offs, HIPERT SRL and Minerva Systems. Our research is focused on next-gen embedded computing platforms and also autonomous systems. We have, for example, 5 autonomous driving cars, laser gate vehicles, delivery bots, and some drones. We are also involved in autonomous racing, such as in the Autonomous Challenge or the F110. We are around 70 researchers for a funding of 10 million euros. Inside Imuko, Unimore is involved in Demo 2, smart sensoring on injected plastic parts, where we provide integration platforms and deployment environment, as well as our expertise to collect and transmit sensors information. Unimore is also involved in Pilot 3, high-speed packaging, where we provide integration platforms and deployment environment, like in Demo 2, but also our expertise in timing guarantees advancement, as well as our expertise in virtualized environment with and without TSN. Now, I will let my colleague Donato Ferro continue the presentation of virtual TSN.
Thanks, Fabien. Hi, everyone. I'm Donato Ferraro, an industrial PhD student working at Minerva System and Unimore. Before I continue, I'll explain two main keywords. The first one is virtualization. Virtualization is a technique of abstracting physical resources to create virtual instances or also virtual machines. The component that enables the virtualization is called hypervisor, and the hypervisor is that component that allows multiple operating systems to run on the same hardware. So probably some of you may have heard about VirtualBox or web player. Basically, they are hypervisors that allow, for example, Windows and Ubuntu to run together on the same laptop. Okay, so but why is the virtualization good? Virtualization helps reduce the amount of hardware resources that are needed. It also allows for you to split your application into multiple virtual machines, improving the isolation between the different tasks. Typically, a hypervisor allows also to allocate an amount of memory and the number of cores for a virtual machine, making the system flexible. So, for example, if I see that one of my virtual machine is not able to complete its task in time with only one core, I can try to add another one and see if with that one it will be able to complete. Okay, so this can also help in finding the optimal resource allocation, as it is usually easy to change these parameters. Moreover, the isolation of resources and also the isolation of the different tasks tasks in my system improve the predictability and reduce the concurrency of my system. So the whole system at the end will result more predictable, and this will help to get this certification, for example. The other key word is time-sensitive networking, also known as TSN. So, essentially, the amount of data that newer sensors generate is increasing, and communication interfaces such as CAN or LIN cannot handle this amount of flows, this amount of data. Hence, to address this problem, embedded systems are incorporating Ethernet communication between sensors and control units of the systems. But standard Ethernet communications are not predictable. So TSN protocols make them predictable by, for example, allocating a budget or reserve a bandwidth limit to different flows, prioritizing the critical ones. This helps to make Ethernet communications predictable. They also scale good because they are highly flexible, but also can still be used with legacy Ethernet connections. Most of the embedded platforms, however, are small and usually does not have multiple Ethernet ports. If we plan to use virtualization for benefiting from its properties, we need a way to share the Ethernet port between virtual machines, but at the same time still applying the TSN protocols. Our solution aims to address this problem. It is called Virtual TSN. As mentioned before, it incorporates the benefits from the virtualization and TSN protocols. So once again, virtualization for better isolation, greater flexibility, resource optimization, and predictability, while TSN protocols for the predictability of the Ethernet communication by prioritizing the critical ones. So let's see how does Virtual TSN work. Virtual TSN runs in a dedicated virtual machine acting as backend and is composed of two components. A virtual switch that allows the communication between front ends and the Ethernet port, a scheduler for the flows that applies TSN protocols such as IEEE 802.1 QAV or QBV, and of course we also need the driver for the Ethernet device and the driver for the inter-virtual machine communications. Our solution uses JLAWS as hypervisor. It also uses its IVU share memory mechanism device for the communication between virtual machines and applies the QAV protocol to the flows. This protocol, the QAV, is a credit-based scheduler that allows you to assign an amount of bandwidth to a flow, so that when the flow is sending data, its credit is decremented, while when other flows are sending, its credit is increased. Just to clarify it a little more, if you have multiple flows in your system and one of them is critical, it is possible to assign the 90% of bandwidth to this flow and the 10% to the others one. In this way, you are pretty sure that the amount of bandwidth that you need for your flow is guaranteed. So let's now talk about JLAWS. JLAWS is an open source static partitioning bare metal hypervisor which has minimal runtime code and does not provide emulation of resources. JLAWS is a bit different from the other hypervisor since it is not able to boot up alone. Instead, it requires Linux operating system and a kernel module. In the top picture, we see this phase. So essentially, the system boots a Linux operating system. We then use this kernel module to add JLAWS directly on the hardware, and hereafter, JLAWS will manage all the resources. After this phase, Linux is now a privileged virtual machine, or also called root cell, with all the resources assigned that can we still use to create new virtual machines, and in this case also called cells. So since JLAWS is a static partitioning hypervisor, it assigns resources one-on-one to the virtual machines, allowing the isolation of software resources such as CPUs, memory, and interrupts, for example. Moreover, for instance, when we create a virtual machine, we detach the CPU from the root cell and assign it to the new one. So, as we can see in the bottom picture, we have an example set up with a Linux OS with Core 1 and Core 2, a bare metal application running on the core 3, and the real-time operating system running on the core 4. JLAUS also offers an inter-virtual machine shared memory device for the communication between virtual machines. This device is seen as a virtual PCI device, and so we have the typical PCI fields. In particular, in bar 0, we find useful register memory such as the ID for the virtual machine in that communication. We can also set its state by writing to this register called state, and doing so we will inform the others that we are ready or not, for example. And the meaning of the state value will depend on the protocol that we want to use for the inter-VMs communication. Another really useful register is the doorbell, which allows us to send an interrupt to one of the VM connected into the device. And so in this way we can, for example, notify a new message. In bar 2 we have the shared memory regions. So we have some memory which is shared between the virtual machines connected to the device. The standards expects to have one state table that will save the current state of all the virtual machines connected to this device, one read-write section where every virtual machine can read and write, and then n output sections where n is the number of the virtual machines connected to the device. So each virtual machine has read-write permission to one output and read to all the others. So for instance, in a system with only 2 virtual machines, VM0 has read and write permissions on output 0 and only read permission on output 1, while VM1 read permission on output 0 and read-write permissions on output 1. To accomplish this design, we had to work on both front ends and back end side. As front end, we support different types of operating systems, Linux and also real-time operating system Erica. We also deployed a bare metal application that was really useful at the initial phase of this deployment. And our backend, the virtual switch, is able to handle all the 3 virtual machines running simultaneously. And also we had to reach high bandwidth with the bare metal driver, and we were able to reach the time guarantees for autonomous scenario. And the other thing is that it is able to handle the life cycle of the virtual machines. So it is able to understand when one virtual machine is ready, when not. You know, I explained before the possibility that the will share memory device gives in order to manage this kind of manage the status of the virtual machines. We made a latency evaluation of the virtual TSN using AMD Xilinx Zinc UltraScale Plus 1 or 2 using the ping tool. We sent 100,000 packets with different size from 64 to 1480, which was the minimum and maximum packet size of a ping, and with an interval of 1 millisecond within one packet and the other. We confronted a JLAUS-based solution, so JLAUS and only one virtual machine with Linux executing ping, and virtual TSN with up to 3 virtual machines in a round-robin configuration. In the first case, Linux directly sends messages over the Ethernet device. In the other cases, Linux virtual machines send messages to virtual TSN that forwards them to the network. As we can see, we have a bit of overhead since we have a communication in the middle. that increases with the number of the virtual machine executing ping simultaneously. But at the same time, the latency is correctly split between the virtual machines, and we can share with still acceptable latency the Ethernet port between the other virtual machines. So we can have different Linux running simultaneously, sharing the same Ethernet port. We were able to test the V-TSN with only 3 Linux virtual machines because the Zinc UltraScale Plus 102 has only 4 Cortex A53 cores. And since we are using a static partition in a hypervisor, JLAWS, we can at maximum have 4 virtual machines. We also compared our solution, the V-TSN, with the Xen-based solution. Xen is another bare metal open source hypervisor. It is able to emulate resources and can have static and dynamic allocations. We set it up so that it reflects the V-TSN. So we set it up in a static partitioning way, where we have only one virtual machine that is doing the virtual switch, and others that are like reflecting what we have done for the V-TSN. So one Xen virtual machines manages the Ethernet device and receives data from the others. We repeated the experiments with Xen, and as shown in the graph, the Xen-based solution performs worse than all the other V-TSN cases. So here in the picture we can see that our solution is under the 0.1, while Xen is always on top of it. We also evaluated the bandwidth utilization for both TCP and UDP protocols and confronted it with no virtualization, only JLAWS and one virtual machine, only Xen and one virtual machine, the virtual TSN and up to 3 virtual machines, Xen and up to 3 virtual machines. As we can see in the red box, we are currently losing some megabytes in the communication between, let's say, the JLAWS based solution and our. But even in this, but at the same time, even in this case, we perform better than the Xen based solution, and we split correctly the bandwidth between the virtual machines. Where can V-TSN be used then? In all the industrial sectors, from the automotive to the avionics, maritime, agriculture, manufacture, where we have different highly connected clusters, different kind of electronic control units, chiplets that require low latency but still high-speed networking. In some business cases where we have different rigid scenarios, we need the flexibility of TSN networking. We need the predictability of the inter-virtual machine communication. We want to reduce the power utilization and the costs. So, as I was saying initially, the virtual TSN allows you to reduce the amount of hardware that is needed. So, you need less platform, and this also results in less cost. So once again, our solution aims at having one single TSN endpoint that can be shared among multiple virtual machines, preserving the determinism and the predictability, and also that allows to shape the traffic of the inter-virtual machines. To accomplish this design, we had to work on both front ends and back end side. As front end, we support different types of operating systems, Linux, and also real-time operating system Erica. We also deployed a bare metal application that was really useful at the initial phase of of this deployment. And our backend, the virtual switch, is able to handle of all the three virtual machines running simultaneously. And also, we had to reach high bandwidth with the bare metal driver, and we were able to reach the time guarantees for autonomous scenario. And the other thing is that it is able to handle the life cycle of the virtual machines. So it is able to understand when one virtual machine is ready, when not. I explained before the possibility that the I/O share memory device gives in order to manage this kind of manage the status of the virtual machines. As future challenges for the V-TSN, we want to port it to one of the real-time core. In this way, we can manage more virtual machines. We want to extend the amount of platform that we support. So instead of the single Taskade Plus, also one of the NVIDIA platform, for example. And we want also to implement other TSN protocols, such as QBV. We want to add a kind of virtual DDS support on virtual TSN so that we will be able to manage DDS communications. This because ROS or ROS2 is one of the most used framework to design robotics application, and it uses DDS-based communication. So this will allow our virtual TSN to support also different kind of applications. And moreover, another interesting topic is that DDS allows some quality of service parameters, for example, the reliability of the communication. We would like to explore the possibility to combine DDS quality of service with TSN protocols. And in order to understand, for example, the overhead that we have when we combine both of them, but also if the communication will be more reliable if we combine both of them, and so we increase the safety of the system. With this, I ended this part. I let Fabian continue and conclude the presentation. Thank you for your attention.
Just to provide you an idea of where we are gonna use our virtual TSN solution, the virtual TSN was involved in the design patterns of dual zone architecture for autonomous driving use case, which is described in the time-sensitive autonomous architecture paper. In this paper, we have described and evaluated the importance of the utilization of TSN protocols in real-time applications like autonomous driving systems. In this paper, we have also evaluated our time-sensitive autonomous architecture solution on both simulated environments and real environments using a Maserati Quattroporte. The design of these architectures involves different technologies such as virtualization, virtual TSN, real-time operating system, and different kind of DDS. We also used virtual TSN inside the pilot 3 of Imoco, which is based on industrial case scenarios, and where we provide a high determinism, high acceleration with virtualization. Here is the resources used to make this video. So you can find first the time-sensitive autonomous architectures paper, but also some link through TSN providers, Soki and Orolia, a link through the hypervisor we used, so the Jailhouse project, and a link through the Minerva website, one of the spin-off of Hyperlab. Thank you very much for watching this video.